You think you know what energy is. You use the word every day. You say you're low on energy. You pay for energy. You hear about energy crises, energy drinks, renewable energy. The word is everywhere. So explain it to me. What is energy? Most people say something like this. Energy is the ability to do work. Energy is power. Energy is this invisible stuff that makes things move and happen. Wrong. All of it. Those aren't explanations. Those are just renaming the mystery. You replaced one word you don't understand with other words you don't understand. That's not knowledge. That's vocabulary. Here's the thing that's going to bother you. Energy is not a substance. It's not a fluid. It's not little blobs of stuff flying around. You cannot hold energy in your hand. You cannot put it in a jar. You cannot point to it and say, there, that's energy. Energy is a number. That's it, a number. A mathematical quantity that we calculate. And when we calculate it correctly, it stays the same. Before something happens, we add up all the numbers. After something happens, we add up all the numbers again. Same total, every single time. No exceptions in ordinary physics. That's energy conservation. And most people think they understand it. They don't. Because most people think energy conservation means there's a fixed amount of stuff in the universe and it just moves around like money changing hands. Someone gains $1, someone loses $1. Simple. But energy isn't money. Energy isn't stuff. Energy is a bookkeeping trick. The most powerful bookkeeping trick in the history of science. And the reason it works, the deep reason, is so strange and so beautiful that it changes how you see the entire universe. Let me show you. Start with something simple. A pendulum. A ball on a string, swinging back and forth. At the top of its swing, the ball stops for an instant. It's not moving. Then it falls, speeds up, reaches the bottom of the arc, moving fast. Then it climbs back up on the other side, slows down, stops again, back and forth. Now at the top, the ball has height. It's above the lowest point. We assign a number to that height. We call it potential energy. The formula is simple. Mass times the acceleration due to gravity times height, mgh. For a 1 kilogram ball, 1 meter above the bottom, that's 1 times 9.8 times 1. That's 9.8 joules, a precise number. At the bottom of the swing, the ball is moving fast. We assign a number to that motion. We call it kinetic energy. The formula is 1/2 times mass times velocity squared. If that 1 kilogram ball is moving at about 4.43 meters per second at the bottom, the kinetic energy is 1/2 times 1 times 4.43 squared. That's 9.8 joules. Same number. Exactly. At the top, 9.8 joules of potential energy, 0 kinetic energy. At the bottom, 0 potential energy, 9.8 joules of kinetic energy. The total is always 9.8 joules. At every point in the swing, potential plus kinetic equals 9.8 joules. The numbers always add up. You say, of course, energy is conserved. The energy changed from potential to kinetic. Everyone knows that. But stop. Think about what you just said. What changed from potential to kinetic? What moved? What flowed? Nothing. Nothing flowed anywhere. There is no substance called potential energy that transformed into a substance called kinetic energy. What happened is that one number decreased and another number increased by exactly the same amount. It's bookkeeping, pure mathematics. We calculated 2 different quantities using 2 different formulas, and their sum stayed constant. This is what people get wrong about energy. They think conservation means something is preserved, like preserving fruit, like there's a thing called energy, and it gets passed around. No. Conservation means the total of a specific calculation doesn't change. That's all. It's a mathematical fact about the universe. And here's what makes this really strange. We don't actually know what energy is in any deep sense. I said this in my lectures, and I meant it. We have no knowledge of what energy is. We don't have a picture that energy comes in little blobs of a definite amount. It's not like that at all. We just know that there's a numerical quantity which doesn't change when something happens. It's like having a child with 28 blocks. You count them at the end of the day. Sometimes you find 25 in the room. You look around. 3 are under the bed. 25 plus 3 is 28. The next day you find 22. You look everywhere. 4 are in the box. 2 are in the bathtub. 22 plus 4 plus 2 is 28. Every single day, no matter how cleverly the blocks are hidden, the total is 28. That's energy conservation. We don't know what the blocks are made of. We don't know why they're exactly 28. We just know that the count always works out. And in physics, that count involves different formulas for different situations. Kinetic energy, potential energy, thermal energy, each calculated differently. But the total is always the same. And now the real question, the one that changes everything. Why? Why does this number stay constant? Why should the universe care about our bookkeeping? Here's where everything changes. In 1918, a mathematician named Emmy Noether proved something extraordinary. She proved that every conservation law in physics comes from a symmetry, not a loose poetic connection, a rigorous mathematical absolute connection. If the laws of physics have a certain symmetry, then there must be a corresponding quantity that is conserved, no exceptions. Let me make this concrete. Think about space. You do an experiment in New York. You do the exact same experiment in Tokyo. You get the same results. The laws of physics don't care where you are. New York is not special. Tokyo is not special. The laws are the same everywhere. That's a symmetry. We call it spatial translation symmetry. The universe looks the same no matter where you stand. Noether proved that this symmetry, this fact that location doesn't matter, directly produces conservation of momentum. Linear momentum is conserved because the laws of physics are the same everywhere in space, not similar, not approximately, mathematically identical. The symmetry generates the conservation law. Now think about direction. You do an experiment facing north. You do the same experiment facing east. Same results. The universe doesn't have a preferred direction. That's rotational symmetry. And Noether proved that rotational symmetry directly produces conservation of angular momentum. Spinning things keep spinning because the universe looks the same in every direction. Now here's the big one. Think about time. You do an experiment today. You do the same experiment tomorrow. Same results. The laws of physics don't change from one day to the next. That's time translation symmetry. The universe today operates by the same rules as the universe yesterday. Noether proved that this symmetry, this fact that the laws don't change over time, is exactly what produces conservation of energy. Energy is conserved because the laws of physics are the same today as they were yesterday and will be tomorrow. Stop. Let that sink in. Energy conservation is not some separate rule imposed on the universe. It's a consequence of the universe being consistent over time. The reason the numbers always add up is that tomorrow's physics is the same as today's physics. If it weren't, if the laws changed over time, energy would not be conserved. This is not philosophy. This is theorem. Proven. Rigorous. In quantum mechanics, the connection is explicit. The time evolution operator commutes with the Hamiltonian. States with definite energy maintain that energy because the system's rules don't change with time. I said this in my lectures. In quantum mechanics, it turns out that the conservation of energy is very closely related to another important property of the world. Things do not depend on the absolute time. Let me make this even more concrete. Think about what would happen if the laws of physics did change over time. Suppose gravity got stronger every year. A ball you dropped in 1980 would fall slower than a ball you dropped in 1985. Your pendulum would behave differently from one year to the next. The numbers you calculated at the top of the swing and the numbers you calculated at the bottom wouldn't match up anymore. The bookkeeping would fail. Energy wouldn't be conserved. Not because something went wrong with the experiment, but because the universe itself changed the rules between measurements. The fact that you can do an experiment in a lab in 1892 and get the same result in 1975 is not obvious. It's not guaranteed. It's a feature of this particular universe. And that feature is why energy conservation works. That's the deep answer. Energy is conserved because time is symmetric. Momentum is conserved because space is symmetric. Angular momentum is conserved because direction is symmetric. The universe's symmetries are the reason our bookkeeping works. Now here's what makes energy so confusing. The number shows up everywhere, wearing different costumes. Kinetic energy, potential energy, thermal energy, chemical energy, nuclear energy, electromagnetic energy, mass energy. People think these are different kinds of stuff. They're not. They're different terms in the same equation. Think about what happens when you strike a match. Before you strike it, you have chemicals on the match head: phosphorus, sulfur, potassium chlorate. The atoms are arranged in a specific way. The electrons are in specific configuration. We can calculate a number for that arrangement. We call it chemical potential energy. You strike the match. Friction heats the chemicals past their activation energy. The atoms rearrange. New molecules form. The electrons settle into lower energy configurations. The number we calculate for the new arrangement is smaller than the number we calculated for the old arrangement. Where did the difference go? Into kinetic energy of atoms. The atoms are now jiggling faster. We call that heat. The heat excites electrons in atoms. Those electrons jump to higher energy levels, then fall back down, emitting photons. We call that light. At every step, the total number is the same. Chemical energy decreased. Thermal energy increased. Radiant energy appeared. The books balance. Not approximately. Exactly. We've measured this to extraordinary precision. Calorimetry experiments confirm it. Joule's original experiments in the 1840s measured the mechanical equivalent of heat to within a few percent. Modern measurements confirm conservation to many decimal places. And then Einstein showed us the most dramatic disguise of all. Mass itself is a form of energy. E equals mc squared. The mass of an object multiplied by the speed of light squared gives you a number. That number is energy. A 1 kilogram object sitting perfectly still has 89,875, 573, 681, 764 joules of energy locked in its mass. That's about 90 quadrillion joules from 1 kilogram. That's roughly the energy released by 21 megatons of TNT. This isn't theoretical. This is measured. Nuclear reactors convert a tiny fraction of nuclear mass into kinetic energy of particles. The mass of the products is measurably less than the mass of the fuel. The missing mass shows up as energy, exactly as the equation predicts. We've confirmed this in thousands of nuclear reactions, particle collisions, and radioactive decays. The books always balance. Here's a specific example. When a neutron is absorbed by a uranium-235 nucleus, it splits into barium-141 and krypton-92 plus 3 neutrons. If you weigh the products, they're lighter than the original uranium plus neutron by about 0.186 atomic mass units. That missing mass, multiplied by c squared, gives you about 173 million electron volts of energy. We measure the kinetic energy of the fragments, 173 million electron volts. Exactly. Every nuclear power plant on Earth operates on this arithmetic. Every nuclear weapon ever detonated confirmed it. The missing mass becomes kinetic energy of particles, becomes heat, becomes the electricity in your house. The number never lies. Now here's what everyone gets wrong. Here's the part that should genuinely break your brain. Energy conservation is not universal. Wait, let me say that again. Energy is not always conserved. I know. I just spent all that time telling you it's one of the most fundamental principles in physics. And it is. In ordinary circumstances, in your lab, in your house, on Earth, in the solar system, energy conservation works perfectly. But on cosmological scales, in the expanding universe, it fails. Remember what I told you. Energy is conserved because the laws of physics don't change over time. That's the symmetry. But here's the problem. The universe is expanding. Space itself is stretching. And that means the universe today is not the same as the universe yesterday. Not because the laws changed, but because the stage changed. The geometry of space-time is evolving. Think about light traveling across the universe. A photon is emitted from a distant galaxy. It has a specific wavelength, a specific energy. E equals h times c over lambda. Planck's constant times the speed of light, divided by the wavelength. That's a precise number. Now that photon travels through expanding space for billions of years. As space stretches, the photon stretches with it. Its wavelength gets longer. We call this cosmological redshift. The photon that was emitted as ultraviolet light arrives at your telescope as infrared. Its wavelength doubled, its energy halved. Where did the energy go? Nowhere. It didn't go anywhere. It didn't transfer to something else. It didn't heat up space. The energy is simply less than it was before. This should shock you. In every other context in physics, energy that disappears from one place shows up somewhere else. That's what conservation means. But cosmological redshift violates this. The photon lost energy and nothing gained it. This is not a small effect. The cosmic microwave background radiation, the oldest light in the universe, was emitted about 13.8 billion years ago, when the universe was roughly 3,000 degrees Kelvin, hot, glowing orange. That radiation has been traveling through expanding space ever since. Today we measure it at 2.725 Kelvin, nearly absolute zero. Those photons have lost more than 99.9% of their energy. Where did it go? Nowhere. It didn't go. The universe expanded. The symmetry broke. The energy decreased. And it works in the other direction too. Think about dark energy, the mysterious force accelerating the expansion of the universe. As the universe expands, more space appears, and that new space comes with its own dark energy. The total dark energy in the observable universe is increasing. Where is it coming from? Nowhere. It's not coming from anywhere. Again, global energy conservation simply doesn't apply. The reason is exactly what Naiva's theorem predicts. The expanding universe does not have time translation symmetry. The universe at one moment is geometrically different from the universe at the next moment, because space itself has expanded. The symmetry that guarantees energy conservation is broken. So energy is not conserved. This is not controversial. This is standard general relativity. Einstein's field equations describe how matter and energy curve space-time, and how curved space-time tells matter and energy how to move. In general relativity, the stress-energy tensor has a local conservation law. Energy and momentum are conserved locally in small patches of space-time. If you zoom into a small enough region, the curvature is negligible and conservation works perfectly. But globally, for the universe as a whole, there is no well-defined total energy. You cannot add up all the energy in the universe and get a meaningful number. The concept doesn't work in curved, expanding space-time. The gravitational field itself has energy, but that energy cannot be localized. You can't point to a spot and say, this much gravitational energy is here. It's not defined that way. This is what most people, even many physics students, get completely wrong about energy. They think conservation of energy is an absolute unbreakable law of the universe. It's not. It's a consequence of a symmetry. And when that symmetry is absent, the conservation law fails. Let me push this further. There's a principle at the heart of general relativity called the equivalence principle. It says this: locally, the effects of gravity are indistinguishable from the effects of acceleration. Stand in an elevator. The cable snaps. You're in free fall. You feel weightless. For those brief seconds, you can't tell the difference between falling in a gravitational field and floating in empty space far from any mass. Your local physics is the same. Einstein called this the happiest thought of his life, and it's the foundation of everything that follows. This means that in a small, freely falling laboratory, the laws of physics look exactly like they do in special relativity. No gravity, flat space-time, perfect symmetry. Energy conservation works beautifully. You can track every joule. The books balance. But the moment you try to extend that to a larger region, the curvature of space-time becomes apparent. Different freely falling observers disagree about what's happening. The symmetries that held locally break down globally. Two freely falling observers on opposite sides of Earth are both in inertial frames, both experiencing perfect local physics, but they're accelerating toward each other. Their frames don't agree, and when frames don't agree, global quantities like total energy lose their meaning. This is why you can't define the energy of the gravitational field itself. In electromagnetism, the electric field has energy. You can calculate it. It's 1/2 times the permittivity of free space times the electric field squared, integrated over all space. That's a well-defined number. But in general relativity, the gravitational field doesn't have a localized energy in the same way. You can write down expressions that look like gravitational energy, but they depend on your coordinate system. Different observers get different numbers. There's no unique coordinate-independent answer. This is the tension at the heart of modern physics. Locally, everything is clean. Conservation laws work. Symmetries hold. Physics makes sense. But globally, in the full curved space-time of general relativity, things get complicated. Energy becomes slippery. You can define it precisely in some space-times, the ones with time translation symmetry, but not in others. Our expanding universe is one of the others. Now here's something fascinating. Not all conservation laws break in curved space-time. Electric charge is conserved globally, everywhere, always, no exceptions. Why? Because electric charge conservation comes from a different kind of symmetry. It comes from gauge symmetry. Specifically, the phase invariance of the electron's wave function in quantum electrodynamics. This symmetry is local. It holds at every point in space-time independently, and it produces a conservation law that is absolute. This is the deep structure of particle physics. The standard model is built on gauge symmetries. Phase invariance gives you conservation of electric charge and the photon. SU2 gauge symmetry gives you the weak force and the WNZ bosons. SU3 gauge symmetry gives you the strong force and gluons. I spent much of my career working on quantum electrodynamics, the quantum theory of the electromagnetic force. The path integral formulation relies entirely on gauge invariance. And gauge symmetries produce conservation laws that are truly universal, not contingent on the geometry of space-time, the way energy conservation is. So here's the hierarchy. Charge conservation, absolute, everywhere, always. Energy conservation, contingent. Depends on the symmetry of space-time, works locally, fails globally, in an expanding universe. Most people think energy conservation is the most fundamental law in physics. It's not. It's powerful. It's extraordinarily useful, but it's not absolute. The gauge symmetries are deeper. So let me bring this all together. What is energy? Energy is a number, a calculated quantity. It is conserved in any system whose laws don't change over time. This covers almost everything you'll ever encounter, every experiment you'll ever do, every machine you'll ever build, every process in your body. Energy conservation works, but it's not magic. It's not a substance being preserved. It's a mathematical consequence of a symmetry. And when that symmetry breaks, when the geometry of the universe itself changes with time, energy, conservation breaks with it, this is what everyone gets wrong. They treat energy as a thing. They treat conservation as a commandment. But energy is a calculation, and conservation is a theorem with premises. And when the premises aren't met, the conclusion doesn't follow. People want energy to be simple. They want it to be a glowing substance that flows from place to place. That picture is comfortable, it's intuitive, and it's wrong. The real picture is deeper. The real picture is about symmetry, about the deep structure of space-time, about the mathematical architecture of the laws of physics. Note this theorem tells us that every conservation law is a shadow cast by a symmetry. Find the symmetry, and you find the conservation law. Lose the symmetry, and you lose the conservation law. This is why energy isn't conserved in an expanding universe. The universe doesn't have time translation symmetry on cosmological scales. Space is stretching. The geometry is changing. And so the bookkeeping breaks down. Now you might find this disturbing. You might think, if energy isn't even conserved in the universe as a whole, what's the point? The point is that it works where you need it to work. In your lab, in your engineering, in your life, the symmetries hold locally, beautifully, precisely. And the fact that they break globally isn't a flaw. It's information. It tells you something profound about the structure of the cosmos. It tells you that space-time is dynamic, that the universe is not a static stage where physics plays out. The stage itself is part of the show. The geometry changes, and when the geometry changes, the rules change with it. That's not a failure of physics. That's physics at its deepest level. We didn't just discover a law. We discovered where the law comes from, what makes it work, and where it stops working. That's more powerful than a blind commandment you follow without understanding. And this is what separates real understanding from the illusion of understanding. Millions of people can recite energy is conserved. They learned it in school, they passed the test, but they think it's a commandment, like a law passed by Congress. Don't create or destroy energy. Follow the rule. That's not understanding. That's obedience. Real understanding is knowing that conservation comes from symmetry. That symmetry has conditions. That those conditions are met locally, but not always globally. That the universe is more subtle, more structured, more mathematically elegant than any simple rule could capture. When you understand energy this way, you see the universe differently. You see that the laws of physics aren't arbitrary rules. They're consequences of deep structural features of space-time. Change the structure, change the laws. The laws aren't imposed on the universe from outside. They emerge from the universe's own geometry. That's what energy really is. Not comfort, not simplicity, not a substance you can hold, a shadow of symmetry, a consequence of the universe being consistent with itself. And the fact that we figured this out, that a species that evolved to avoid predators on the African savanna managed to deduce the mathematical relationship between symmetry and conservation. That's one of the most extraordinary achievements in the history of thought. Energy is a bookkeeping trick. The most beautiful, most powerful, most revealing bookkeeping trick ever discovered. And what it reveals is not just how the universe works. It reveals why the universe works the way it does. That's the real story. Not comfort, not simplicity, truth,